Thank you very much. Oh, well. Thank you very much for coming. And first, before I start, I want to send a deep, deep thanks to the organizers of this workshop for preparing and educating this audience. I really loved the series of talks. So now I assume you guys know a lot about what FHE is. You know a little bit about delegation. You know I/O. So this is fantastic. So we can actually have some fun. Okay. So yes, I'm going to talk about the problem of delegating computation. It has been one of my obsessions in life. Still is. So let me tell you a little bit about it. So thank you so much, Ron Rothman, for the fantastic talk you gave before me. So you presented the problem already, which is great. So just a quick recap. So we have the way we do computations today is shifting. Now many of our computation is done elsewhere on some cloud. Not only our computation, actually, we store our memory in the cloud. We do our computations elsewhere, and of course, this raises a lot of issues for us as cryptographers. I think the two main issues we considered is the obvious one is privacy. So we don't want the cloud to learn information about our secret data or our secret computation, sensitive computation, but as On said, another serious, very fundamental issue is that of integrity. How do we know that the cloud is doing their computation correctly? And note, so this is going to be the focus of the talk, is on integrity. I want a proof that the cloud did its computation correctly. So even though we're in the Simon Institute, which is for theoretical computer science, I don't really feel like I have to motivate this problem, but still, I will. I thought about this motivation for it because you can say, why do we care about proof of security? We give all our data or computation to Amazon. Don't you trust Amazon? So, most of us may trust Amazon, but there's still issues around how do we know that we're actually talking to Amazon? Okay, maybe we think we're talking to Amazon, but we're talking to some adversary. Or I think in general, to make it kind of widely used, people will be more secured if they knew they could get a proof of security, a proof of correctness, if they wished to. So you don't need to ask for a proof each time, but it's nice to know that you could press a button and get a proof if you wanted to. Okay, so this is going to be the focus of this talk. And note that the interesting thing about integrity, it's not cryptography here. Okay, I'm not interested in secrecy. Okay, just on correctness. It's not a priori. It's not clear that it's a cryptographic problem even. Okay, but as we'll see, cryptography is used to solve this problem. Even though I want to stress again, secrecy is not my concern here. Okay, so this is kind of the classical problem that we're interested in. This is exactly what Ron had. So here's a client. He wants to compute some function f on an input which he knows. Okay, he has some function f and input x. He wants to do this computation. He doesn't have the resources to do it, so he asks the cloud to do it. The cloud computes the function for him, so he computes f of x. But this cloud may be malicious, so he does not trust this cloud, or he does not know that he's talking to the actual cloud he thinks he's talking to, and so he wants a proof of correctness. So I prove that the computation was done correctly. And here are the two important things that we want from the proof. Okay, we want first that verifying should be easy, much, much easier than doing the computation itself. Okay, so how easy? Think about it. Essentially the size of the input and the program. Think of the program as a Turing machine, so it's constant size. So it's essentially the size of the input, not more. And in a minute, I'll address Tal's question from last time. So this is kind of, the best you can hope for. So he has his input, but not in the function. But his runtime should not depend on the runtime of the computation. And how about the cloud, the prover? Well, he needs to do the computation. So T of f is the time it takes to compute this function on input x. So he needs to do the computation. So he needs to run in time T of f, which is the time to do the computation. But ideally, not more than that. Not much more than that. Yes, Jai?
The problem changes a lot if f is not a function, if there are many more than a single accepted answer from the cloud.
Oh, if it's a... So
I don't know. I want
question.
driving route from somewhere to somewhere else. Right. There are a few of them. I'll take any one as long as it doesn't go against the traffic direction.
So in general,
no. So I think okay. So the results we have work for this heading as well. So it's not important that it's let me think about it. No, it is important actually. Sorry, I take it back. It is important. So what you're suggesting, what you're asking, the question you're asking is, what if it's an NP question? Right? So what if there are many answers? So for the question of delegation, if it's a deterministic function or not deterministic function, changes completely. So that's one answer. Another, but what you're saying is actually not quite the same as NP, because you're saying there are many. The answer is not always one if there is a witness and zero if there's not a witness. There just may be many accepting answers.
I think that you can reduce
or maybe
think of the cloud as giving you the answer, one answer, and the language that you're thinking of is x, y, whether it's a valid. It's in the relation, and then you can invoke your protocols. It's a language and everything.
So if you can do it deterministically, then you're right. So if the answer is something that you can deterministically compute from there, then it's P. Then it's the same.
What if it's randomized, but the amount of random
is short?
Very big. I mean, if it's short, then you can just include it in the input.
Right, exactly.
Very big, then it's interesting, right?
It's very interesting. I didn't think about it, but I will. It's very interesting. So please ask. It's good. We'll start to do research here. Okay, so I don't know. It's a very good question. Okay, so this is kind of the standard setting. Okay, but actually, going back to Tal's question from Ron's talk, this is not necessarily the most realistic setting. So as we said, we're not just delegating computation and input X that we know. We're delegating our memory. So, we're giving the cloud our entire memory. And we're asking the cloud to do the computation. So we're giving him our data. This data may be huge. Okay? We can't even store the data. So think of the setting, maybe a more realistic setting, is the setting where we give the cloud our entire data, all our email, we give Gmail all our email, and we keep something, maybe some certificate of our data, some small commitment or some small hash of our data. And now we ask the cloud to compute some functions on my data. But I don't even have my data anymore. All I have is some short certificate or some short commitment of this data. And even in this context, I want to be able to get the result, f of x, and a proof of correctness. And note here that I also added commitment prime to be even more general. I may even want the cloud to do computation that may affect my data. Maybe I want him to update things in my data, delete things in my data. So this now changes the commitment I have for my data. So this function may actually change my data, in which case I want him to give me a new commitment to my data. And still I want to be able to have my guarantees that I can verify very efficiently, and the cloud doesn't need to have much overhead. So let me be a little more specific. What's ideally our goal? So our goal ideally is that the verification time should not depend on this huge data, nor on the computation time. Okay, and by the way, the setting to think of here is you can think of the data as huge, and actually the runtime of F is smaller. So it's a different setting than the traditional delegation setting. So you can think of F as really huge, and the function you compute is some kind of RAM program of this memory. Okay? So ideally, I want the verification time to depend only on some security parameter. So throughout this talk, security parameters kind of hide inside this O. But the O of 1 does not mean constant time. It means essentially time that does not depend on the data. And the function only depends on the security parameter. Okay? So the verification time should be independent of the data and the function. And the time to prove, so what's the time to prove? So now actually it's important in this setting where the data is huge. I want the time to be, I want to think of F, now the function that I compute, as a RAM machine, a random access machine. And in this context, it actually, if you use a Turing machine or a RAM machine, it's very different. Because if you think of the data as being really huge, there can actually be an exponential gap between the two. Okay, think of binary search. Okay, the RAM machine works in log time, whereas If you think of it as a Turing machine, it's linear time. Okay, so when I have huge amount of memory, I want to think of this function as a RAM machine, and I want the prover to run not much more than the time the RAM machine would run. So really, I want the overhead to be only depending on some security parameter. That's my wish. Okay? So, so most of the talk, I'm going to talk about actually the classical setting of delegation. But since I talked about it so much by now, let me start with something new, fresh, to keep me at least excited. So I want to present a new theorem, which is joint work with Omer Panet, where what we do is we construct a two-message delegation scheme for any RAM computations with essentially the properties I promised you. So verifying is independent. The time to verify does not depend on the data or the complexity of the function, and it only depends on the description of the function, but I think of it as constant. And the prover's runtime is not much more than the runtime of the RAM machine. And this is under LWA assumption, learning with error. And thank you, Vinod, for not having. I don't need to talk more about this. Okay, and let me mention that there's been a bunch of works that solved. Okay, now I need to be careful because I don't really understand this related work that well. But feel free to. I'll blame the authors. But I think that there's related work that showed how to achieve this from I/O, but a selective version of this, I think. Where I think the meaning of selective is that you get security from I/O assuming that all the functions you want to compute are chosen before the memory is like a priori fixed or chosen independently of the memory. Yes?
Do these works also get privacy, or are these just delegation, the I/O works?
Justin? Also get privacy. So I don't. Okay, so you can't really get privacy and expect to the running time. I'm not really sure how, because you can't expect to have privacy and No.
Yeah. You can just keep it. I do.
I mean, privacy up to running.
Up to running time, maybe. Okay. Yeah, maybe some pre-processing. Yeah. Okay. Let's continue. Okay, so let's start with the history of this problem. So there's been a lot of work, really nice work. I apologize because I know I'm going to mess up and not reference important works, but sorry. Okay, so the problem we're going to focus on until essentially the end of the 2 hours, most of the time we're going to focus on the classical setting, okay? Where in this setting we think of X as small and the runtime of F as big, okay? And we allow the client to run in time, or the verifier to run in time linear or quasi-linear in the input size. And towards the end of the talk, I'm going to show you how to get the RAM setting or the memory setting. Okay, so let's start. So we want a proof. How do we get a proof? So, when you start thinking about this problem, you're like, okay, what do we have? What can we use? And the first thing that comes to mind is, let's use interactive proofs. We have interactive proofs. This is great. So have the cloud gives us an interactive proof that he did the computation correctly. Thankfully, we have this notion, which was studied in the context of zero knowledge. So it was studied for secrecy, actually, but it has nothing to do with secrecy. It's just, proof of validity. And we have beautiful works that show the power of interactive proofs. We know that you can compute any p-space language using an interactive proof. Okay? More precisely, what we know is any language you can give an interactive proof, but the verifier's runtime depends on the space. Something like linear in the space. Okay? So we can use that to do linear space computations. This is great. However, in this work, they weren't interested. The focus was not on the prover's runtime. And the verifier's runtime is essentially the space, but the prover's runtime is quite awful. It's 2 to the space squared, more or less. So the cloud needs to work a lot in order to do such a computation. Okay, so this is not good for us. We don't want a lot of overhead for the cloud in order to give us a proof. Okay, so several years ago, it was a long time ago, so with Shafi and Guy, we tried to make this interactive proof efficient, where the prover runs time is proportional to the time to do the computation. And we did it, but only for low-depth circuit. In other words, we looked at the function, we thought of it as a circuit, okay? And now the time of the verifier, the runtime of the verifier, grew linearly with the depth of the circuit. Okay, so it's efficient for low-depth circuits, for NC1, for example. Okay, but for very non-parallel computation, this is not a good solution. Okay. And let me actually stop here and mention one of open problem that I've really been obsessed with, and I'd be grateful if someone solves it.
You have to offer $100.
$100. Guy, will you split it with me?
I hope I'll take it from you.
Please do. So, okay, so here's what's the open problem. So we got, so with interactive proof, you can't hope that the verifier will run less than the space, because we know from IP equals P space that you can't do more than that. But can you have the verifier run time proportional to the space and the prover proportional to the time? Why does he need to all of a sudden run time 2 to the s squared? Okay, so I want the prover to be efficient, poly T. Okay, and the verifier poly S. So this is an open problem. Please solve it.
So what's the best known, just to compare?
We know how to do it. So I want an interactive proof where the prover is efficient. Okay, so there's only polynomial overhead. We know how to do it, but only for languages that can be represented, or for functions that can be represented by shallow circuits. So the runtime of the verifier depends on the depth. We would like to do it where the runtime of the verifier depends on the space. So I know that it has to depend on the space. There's nothing I can do. IP equals P space. So the verifier's runtime will be proportional to the space. I can't hope to do better. But I want the prover's runtime to be poly T and not 2 to the space.
So Yael, you know how to do arguments. The question is really what proof.
Yes. So this is for, good. So this is for, note that here when I say proof, it's with statistical soundness. So even an all-powerful prover cannot cheat. That's the notion of proofs. Next we'll go to arguments. So that's what's coming up next. Okay, so most of the focus of work in this area, almost all the focus, has been on trying to get, so the previous solution I showed you was very interactive. Okay, and there's some lower, it has to be interactive in some sense, okay? So with interactive proof, in the solution with Guy and Shafi, the number of rounds was linear in the depth. Okay, and any kind of solution will be, for general solution, will have a lot of rounds of interaction. So the focus, though, in the literature was on trying to get no interaction, or just 2 messages back and forth. So the client gives him the computation, maybe asks some questions, and gets back a proof. That's it. 2 messages. Okay, that's what people wanted, and they wanted arbitrary computations. Okay, so not only low depth and not only P space. They want any computation. Any time T computation, I want proof. So that has been the focus. And if you want to do that, you cannot hope to have statistical soundness, so do proofs, and you have to move to the regime of what's called arguments. So now, if you want to prove correctness of arbitrary computation, you have to settle for computationally sound proofs, which means that an all-powerful cloud or prover can cheat. But as long as he cannot break LW assumption or IO or whatever it is, he cannot cheat. Okay, so the assumption is that this cloud cannot break some cryptographic assumption that we're using. Okay, so Vinod asked for a landscape slide.
That's it?
Enjoy. So, okay, so I'll try to summarize the work that has been done on this topic. There's been a lot of work, and a lot of the works I'm not going to mention, so I'm kind of choosing few works that have kind of mainly the theoretical work I'm focusing on here. I'm not focusing on the more practical work. So there's been a lot of really nice practical work that I'm not going to mention. Okay, so the landscape. So where did this all start? So it started with a work from '92 of Kilian, where he showed how to do it, how to do a delegation scheme with 4 messages. Okay, so 4-message delegation, the only thing he needed to assume is collision-resistant hash function. Great, solved. For 4-message, that's all we need. Okay, so 4-message, client sends a message, get back some hash, client sends queries, get back answer, that's it. Okay. And then started the obsession of getting this with 2 messages. Okay, so just question, answer. Okay, and here's what's known.
So, yeah, quick
Yes.
question. So, for statistical, I guess, soundness, what is the low bound on the round complexity? Is it like, you used to, it has to be interactive, but...
Yeah, so look, you know that it depends on the S, on the space.
Okay.
So that's, so if you have space S, the number of rounds you need depends on S.
So you're saying...
So for constant number of rounds, you're an Arthur Merlin. You can't do more than Arthur Merlin. So that's, I mean, lower bound, I mean under complex, assuming the polynomial hierarchy does not collapse and so on. It's not really a... Okay, so, any other questions? Okay, so Mikali in '94, he followed up, so what he did 2-message delegation, or you can think of it actually as 1 message even, in the random oracle model. Okay, so essentially he applied what's called the Fiat-Shamir paradigm. For those of you who are familiar, for those who are not, don't worry. He applied this paradigm in the work of Kilian. He got essentially a 1 message in the random oracle model, or 2 message where the first is some random hash.
Isn't proving much harder in both of these protocols than
PCP, there's only polynomial overhead.
Okay, but not linear. So it's not
Actually, they have even quasi-linear PCPs. Yes. It depends. You can do it in a way that's quasi-linear. But yeah, actually in this slide, I'm going to show you works that runtime, most of the work, the focus was not on getting the linear, but just polynomial overheads from both sides. But you wanted the client to run in time that depends only on the input, independent of the runtime, but not necessarily linear in the input. And the cloud the overhead should be only polynomial in its runtime, not necessarily quasi-linear. Okay, but here actually was pretty good, the runtime. I mean, you can make it pretty good with new PCPs. Okay, and that's all we could do for a while. Together with Ran, we managed to kind of squash the protocol, the GKR protocol, the protocol with Gan Shafi, and to make it 2-message. So we get 2-message delegation, but again, it's for depth D circuits, and what we needed to assume is computational peer, which I don't want to define. Think of FHE. Okay, so those who don't know what peer is, just think of FHE. Okay.
What does depth D mean?
So okay, good. So what we do is delegation scheme for any circuit. So take your function, think of it as a circuit. Suppose the depth of the circuit is D. The verify runs in time D. Okay, so for shallow computations, for NC1 type computations is great. For very deep computation or computation that cannot be parallelized efficiently, it's bad. Okay, and that's it. That's all we knew for a while. There have been some works in the pre-processing model. So the pre-processing model.
This work with Ron, is it for NC or?
It's for NC, or more generally, you can think of like linear depth. But
Fine, but the thing grows with it.
the thing grows with the depth.
Supposed to kill it and Mikali, which is for NP.
Yes, actually, Killing kind of for NP, not even for P. I'm going to mention that. But yes, exactly. Yes. With these work, you can also do non-deterministic computations. Here, we're stuck with deterministic computations. Okay. And then there was some attempt, a lot of really nice works, trying to do delegation, assuming pre-processing. So what is pre-processing? They say, you know what? The client maybe once will work hard and keep some secret or some state or something, and then he'll never work hard again. Okay, so that was the way people relaxed the model, and there's been really nice work, starting with Gennaro, Gentry, and Parno, very nice work, doing 2-message delegation, assuming FHE, for any deterministic computation. Okay? There was a slight negative in this work, and the follow-up works mentioned above, which is there was this rejection problem. What is the rejection problem? The problem was that once the cloud knew that the client rejected his computation, he learned something about the secret state of the client, and then he could cheat. So it's okay as long as the cloud never rejects you. But once the client, as long as you don't reject the computation, the proof. But once you start rejecting the proof, you need to do the pre-processing all over again. Okay, so that was a slight negative, and then there's work trying to get around this. You know, they don't want this. You want once and for all to do pre-processing, and that's it. And then there was a really nice work of Paulo Rekova and Vinod that it was also the pre-processing, but their work was publicly verifiable. So publicly verifiable, everybody knew if you rejected. There was this rejection problem went away, okay? Because you don't need to keep state. Everybody can check whether you're verified or not. It can check whether you accepted the proof or not, and this problem goes away. And all they need to assume was ABE, attribute-based encryption, which is a standard assumption. We know how to do it under LWE. Unfortunately, we know how to do it under LWE only for, again, bounded depth. So you need to say ahead of time what the depth is, and the verifier runtimes grows with the depth. So same issue as here. Okay? But the good thing about this work is that it's publicly verifiable. And let me just mention, these two works up here are also publicly verifiable. These are not. Okay? And then there were really nice works trying to get publicly verifiable delegation for any language. Actually, their works was for even non-deterministic languages. Okay, but they needed to rely on the knowledge assumptions. Okay. And again, I want to mention this work was for non-deterministic languages. The works up there were for non-deterministic languages. The rest were for deterministic languages. Okay, so in the pre-processing, we can do, there's a rejection problem here, which kind of sucks. If you come up with better ABE schemes, we can, do arbitrary. And then if you're willing to assume knowledge, you're golden. You can do anything. Pre-processing. Okay.
So this sequence of works is comparable to Kalai 94, right? I mean, in the sense that, it's like, in Silvio's case, he just assumed the random oracle model in a sense, and these are much more.
I mean, what do you mean comparable? They require pre-processing, which is worse. He didn't use pre-processing, so this is worse. On the other hand, random oracle model is.
Knowledge of exponents. I mean.
Well, people that did the knowledge exponent think of it as much better than random oracle, so don't say that. And you'll get in trouble. Yes.
So if you were willing to live with 4 messages.
Yes, then.
Everything is possible.
Yes.
And from this point of view of practical performance.
It's a good question. Actually, for a while we were obsessed not only with, we were really obsessed with 2 messages, right? So we have 4 messages, we're not happy, we want 2 messages. And we worked really hard. And then, it turns out that in practice, a lot of times they actually implement the complete, interactive solution that requires many, many rounds. So it's a good question. It depends. I'm actually not an expert in practice, so I don't know. When I talked with Eran Tomer, he says that non-interactive solutions are very, very important. When I talk with other people, they say that no, who cares about interaction? It's not a big deal. So maybe people who are more applied can.
94 in comparison with the snarks.
Hmm?
How did you think this Kalai 94 in comparison with the snarks?
It's very, very efficient. It depends on the PCP you're using, but I think by now we have very efficient PCPs. So
So why are everyone implementing snarks, but not like, for instance, like Kalai 94?
So I think in snark the main thing is to implement the PCP. The hard thing of the snark implementation is the PCP. I think I'm not sure, but I think most of the work there, maybe someone can correct me if I'm wrong.
There's also an advantage in terms of zero knowledge. With the snark literature, they also get zero knowledge properties for their NP proofs.
No, but you can do that too.
They get it directly
Type
from
of
the
PCP.
assumptions.
So standard traditional PCPs where you query individual symbols are yet to be made more practical, so they're quite inefficient in practice, and this was replaced by linear PCPs. So all of the from Jens Roth and actually earlier derivatives, but all this recent line of works replaced the classical PCP by linear PCP.
Right.
Much linear and can be compiled using
Exactly.
crypto into snarks.
Right.
It's dominated the implementation work.
Exactly. That's what, so I think the main work in implementation in the snark thing is actually the PCP, coming up with good PCPs. So.
So I was trying to understand the difference between the two, right? I mean, so the consensus seems that the thing on the bottom right
Yeah.
is more efficient, concretely more efficient than just doing you know.
Yeah, this does not actually. This work is not the snark. This does not rely on PCPs. This is in pre-processing. It's something else. So this is not what Elaine, you weren't asking about this, right? Snarks.
Yeah, the GDPR one. That one is the snark one.
Yeah. So, oh, you call this a snark? Sorry. Okay, no. So, I don't know, Craig.
Yeah, I mean, the idea is that the concrete efficiency is much better.
PCP. Okay, but this work does not rely on PCP because it's in pre-processing. So maybe I'll finish. I want to mention some more work, and then I'll go also. So, okay.
Less efficient than like GDPR?
I think so. Yes.
GDPR
Yes.
is basically based. What I meant by linear PCP is like the PCP string is a vector, and you can make linear functions. That's the underlying PCP object, which
I see what you're saying.
much more efficiently.
I see. So Yuval said that the PC, what you use here is kind of a linear PCP. That it's what's the query complexity of that PCP?
Well, you can make it as low as one query over a big field, but I think in GDPR it's like 3 or 4. Or 5.
So you just assume that the
That's the information theoretic object that's under the hood in GDPR and the growth.
that the cheating cloud can only do linear computation, essentially. That the cheating cloud can only do linear.
Yeah, it's both the honest.
Both the honest and the cheating. Yeah, and the cheating. Okay, so so then there was. Sorry, I didn't talk about these work. There were works on. So this work was doing pre-processing, but then there was a lot of work trying to get rid of the pre-processing. There were work on trying to do it with extractable collision-resistant hash functions. So this is again a knowledge assumption. And then there was a really nice work of Bitansky and friends that did it publicly verifiable. So two message, publicly verifiable. But again, he needed to assume knowledge assumptions. Oh no, what happened to our one message? It got deleted. Oh, you're right. Okay, never mind. Okay, so what do we have here? So we have for NP, if you assume knowledge, you're golden. Okay, you get everything you want, but you need to assume knowledge. What if we want to do standard assumptions? So I want to mention what I'm going to focus on is a work with Ron Rothblum and with Ran Raz, where we do two-message delegation, assuming computational peer, or again, for this talk, just think of FHE. But it's only for deterministic computation, so not NP. Okay, and I want so this is the focus, but I want to mention follow-up works after this. So there's a lot of nice work. Sorry for making you guys so small, but there's just too many of you to fit. So there's really nice work on getting that do actually succinct garbling, and in particular they get public. So this is not publicly verifiable. They managed to get it publicly verifiable under I/O. Or there's also really nice work of Omer and Guy Rothblum who do it under a specific multilinear map assumption. A kind of standard, as much as you can say standard to multilinear maps, but...
Knowledge of exponent is non-standard and I/O is standard?
Yeah, no, I don't want to say that. So yeah, let me just say, I/O, knowledge of exponent, falsifiable assumption in multilinear maps. No good, no bad, no ugly. Okay, so sorry, I'm gonna skip this. This is a bug. Okay, so so back to Elaine's question about practice. So there's been a lot of practical work on this topic. I'm not an expert on the practical side, and the practice side of things, but. Let's see, so you have here Mariana, you have Craig, you have a lot of people here you can ask. Oh, Wowfish. So, ask your friends. But let me just say one thing. Let me just say one thing that's, amazed me. That here's a quote from one of the papers on the topic, that these, schemes are sufficiently mature to deploy in real cloud computing systems.
Is there a not?
But I can quote. At least I have something to quote. So, yes.
They're all good guys, but that quote is false.
Don't say that. Okay.
Generic construction with the quote, is it the special purpose construction or generic construction?
Well, they have both there. So they have both generic. I mean, they have a specific construction for specific functions, and then they have.
So the quote is for the special purpose one or for the generic?
The most efficient in that line is Thaler 13, which descends directly from the one before it, and even that, it's like awesome, but it is not, like, that quotation does not.
It's false. Okay, let's continue. Okay, so this is the problem I'm gonna focus on. Okay, so so we saw with interactive proof there's so much we can do. Okay, we can't hope to get general results from that. We're stuck with space. We want general result. So the first idea, let's go back to our origins. What other tools do we have to play around with? So the immediate extension of interactive proofs is multi-prover interactive proofs. So it's a notion by Beno, Goldwasser-Kilian, and Wigderson. What is a multi-prover? It's the same thing, but now we assume there's two provers or more than two provers. Okay, and these provers we assume they do not interact. So before they can, talk, they can decide on strategy, but once the proof starts, they go to different rooms. The verifier sends each one a query, gets a response, and based on that decides whether to accept or reject. Okay? So this is a proof model. Again, the motivation for this came from zero knowledge. Their goal was to do information theoretic zero knowledge, which they did. I'm not going to talk about zero knowledge here, but then there was a work by Faulkner and Lund that showed a remarkable result that any proof can be made exponentially shorter if you only had two non-interactive provers. In other words, suppose you wanted to prove some statement that you needed to compute in time t. T is huge, okay? All you needed, the amount the size of Q1 and A, of the queries and the answers, is only polylogarithmic in t. And even the best ones are even log t. But think of polylog. Okay, so exponentially shorter. And here's the precise statement. Any t-time computation has interactive proof. Here, even the prover runtime is efficient. Only polynomial blow up. And this polynomial can be made pretty close to t. And the verifier's runtime is great. It's only linear up to some polylog terms, or you could put here O tilde of x. And the communication is also very small. Great. Now, maybe I'll stop here for a second and tell you, why do they have so much power, these two non-interactive provers? What gives this model its power? Intuitively, the way to think of it, think of suspects. Okay? Someone committed a crime. If you have two suspects, you put them in different rooms, they can't communicate, they can't cheat. You're very easily going to catch them because they don't know what they're going to be asked. And, you can, if you have only one suspect, he can lie. How are you going to catch him? Okay, so that's kind of the, the intuition. And really, that's how the proof works, like a bunch of consistency checks. That's how the proof works. You check him, and then you check, is he consistent? Is he consistent? It's really like suspects. Okay. And then I want to mention a really nice work of Faulkner, Rumpel, and Sipser, that they showed, what? If the communication, if the proof is so short, why do you need the provers? Why not forget about the provers? Ask each prover to tell you his answer to each and every query he may possibly ever be asked. If the questions are of size log, think of log for a second, then the proof is size polynomial. So just write your answers to each and every query. The other prover does the same. Go away, I don't need you, and I'm just going to query this proof in a few. So I'm just going to ask, Q1, Q2, done. And this gave rise to a really, really beautiful, celebrated PCP theorem that shows that actually any proof can be converted to such a proof that's probabilistically checkable. Okay, so you can take a proof, you can convert to another proof of almost the same size. So there's been a lot of work trying to improve the parameters, and by now we know that any proof can be converted into a probabilistically checkable one of essentially almost the same size that can be verified actually by reading only constant number of bits. Okay, and you can, if you read 3 bits, you can be convinced with probability, 7/8 that the proof is correct, and then you can repeat. Okay, so why am I telling you? So first, it's beautiful. Why not? You should know about these results. But how can we use them? So, a priori it seems, well, you can't. I'm not giving you 2 clouds, so what does it help you that you have 2 proven interactive proofs? I have only 1 cloud. And for this PCP to be useful, they need to put this huge PCP. This PCP, the size of the proof is at least the size of the original proof. It's big. It's like the computation. So, you need to put it somewhere, and then you can access it. But where are you going to put it? You don't trust the cloud. So the cloud, where's the cloud going to put it for you? You don't have the memory to store this thing. So it seems a priori maybe not useful, but it turns out it's very useful. So let me show you first the use of PCP for delegation. So this was first used by Kilian, and Kilian's idea was use crypto. So again, we're not trying to hide, but still crypto is very useful here. Use crypto. How are we going to use crypto? The idea is the cloud is going to compute this long PCP. So he's going to take the computation. He's going to convert this computation to a probabilistically checkable one. Okay, so this is the PCP. And then he's going to send the client the answer, f of x, with a hash of this PCP. Now, this hash is a commitment. It's binding. Okay, so he gave him, think of it as a collision-resistant hash. So now, effectively, intuitively, it's like putting this in the sky somewhere. This is the first round, and then the user can ask the queries, get back the answers. And one can prove that it's sound. And that's Kilian's work. And actually, all these works are based on this paradigm. You commit to the PCP, and then you ask queries. So this one is interactive, this one uses random oracle to reduce the interaction, and this uses some, more machinery to reduce interaction using knowledge. But that's essentially kind of the initial idea behind these schemes. Questions? Yes?
So this might be pretty naive, but can you use this reduction for 2 clouds by asking one cloud the same question in 2 different ways?
That's a very good question. So I'm going to get to that. That's great. Yes, the answer is yes. And that's okay. So thank you very much for the question. The question was, you have 1 cloud. Can you somehow, you want to have 2 clouds, you have only 1. Can you somehow give the 2 queries, somehow ask only 1 cloud in some other way? And the answer is yes, that's exactly what we're going to do. Okay? So now I'm going to show you how to use kind of the multi-prover interactive proof to get delegation. Okay? And actually, as we'll show in the next hour, multi-prover interactive proof and PCPs are really the same. So I showed you how any multi-prover interactive proof kind of can be, or 2-prover interactive proof, multi-prover is the same, kind of leads to PCP. PCP also leads to multi-prover interactive proof, and I'm going to show you that in the next hour. We're going to use that. Okay, so now let me show you the idea kind of that underlies these work. I'm so sad because there's so beautiful ideas in the other work that I really wanted to talk about, but I feel like there's just so much I can bombard you with, so I'm going to focus on this. Okay, so the theorem I'm gonna focus on is the theorem from the work with Ran and Ron, which says that Ron Rothblum and Ran Raz, which says that any deterministic time computation, this is only good for deterministic computations, it has a 2-message delegation scheme, assuming learning with error. The LW assumption, prover runtime is quadratic, verifier runtime is quasi-linear, and the communication is depends only on the security parameter. And I want to point out. Everywhere, our works where I said LWE, I cheated. Sorry. Almost LWE, but not quite. I needed LWE with that sound that's secure against quasi-polynomial time adversaries. And actually, it's a double cheat. So if the language is polynomial time, then I need just quasi-Pauli security. Of course, if the language is exponential, then it's unavoidable. You need exponential or sub-exponential security. Okay? But for this talk, forget it, because it's going to be high level enough that you won't even see. Maybe I'll mention where the quasi-Pauli comes in.
Yeah, the one is polylog or into the epsilon?
It's security parameter.
Because previously you mentioned something like
with a polylog. What? Yeah, so sorry, that polylog should have been O tilde of 1. So, this O tilde of 1 just hides the security parameter. Now it's up to you. You can take the security parameter to be polylog, and then this is great, everything is very small, but you rely on harder and stronger assumptions. You can take the security parameter to be bigger, and then you rely on better assumptions, so I'm leaving it vague. Okay?
Hardness, then you need you can
exactly, that's what I said. If you want quasi-Pauli hardness, you need the security parameter to be polynomially related to the time. Yes?
So the difference between this and the new result is t squared versus t? Or there is something else?
Oh, there's a lot of other. T is 1, but the main difference is that the verify runtime it's for memory delegation. This is what I'm showing now is not the memory setting. Yeah, but the RAM thing, if you want, you can think about the RAM result in this setting, where you don't care about RAM and the input is small, and you get improvement even for this setting. You get rid of the t squared to t.
Just to make sure, I think the LWE star can be DDH star, can be anything that implies PIR star.
Yes, it can be exactly. It can be DDH star. It can be Yes.
Polylog PIR or?
I need the PIR. I need depend on the security parameter. It's the same. Yeah.
So this is for circuits or RAM?
This is for Turing machines. The RAM, we have similar results for RAM that I'm going to show later, but for now I'm going to focus on the Turing machine results. I always model Turing machine. I never go to circuits, but Turing machine circuits are very similar. The RAM is kind of the difference in the RAM is that you have random access to the memory, and the memory can be huge, and the verifier doesn't even look at the X. He gives away the X ahead of time, and the cloud can do computations on this X, and the verifier runs in time, that doesn't even depend on the X. But we're going to save that to the end. That was just a teaser, kind of. Okay. So let me give you the outline of how we get this. So the starting point is the multiprover. We have multiprover. Let's already use this. But unfortunately, we have only one cloud. So what are we going to do? We're going to follow a really nice approach of Yael et al. That suggests for us a way to simulate many provers using just one prover. So this is kind of a way heuristic to do delegation. Unfortunately, this heuristic as is does not work. And that was pointed out by a very nice paper of Duok et al., in which they found some subtle bug with this approach. And what we do, we show that actually you can get around this bug if you use multi-prover interactive proof that have stronger soundness. So what is the stronger soundness? If it's secure not only against local cheating provers that just, we said that the cheating provers are in different rooms, they can't interact. Each cheating prover acts locally based on his own query. That's the model. Now I'm saying, well, if I'm also secure against stronger cheating provers that are not quite local, but are still no signaling, which I'll explain what that is, if I have that, then I can simulate that to get one prover. So if I start with an MIP that's secure against stronger adversaries, not only local adversaries, but slightly stronger adversaries, then we get, I can simulate a single prover and it works. So I'm going to explain what this no signaling strategy is. This is Einstein. It's inspired by him. I even have him as how many people here have a citation, cite Einstein in their work? Oh, I'm impressed. Oh, you're a physicist. So? Okay, so how do we go from two provers to a single prover? This is the idea. The first idea is, well, you have only one prover, send in the two queries. Send the same prover the two queries, get back the answers. Well, this turns out this is really not sound. Okay, because think again of the two suspects. If you give the same suspect the two queries, come on. He can clearly cheat. So the idea of the Yael paper was give it to them encrypted. And encrypt each query under a totally fresh, independent public key. Okay, so put this one in one box with one public key, put this lock the other query in another box with another public key, and send it to the cloud. Now this is an FHE. Of course, they didn't have FHE then. It was before Craig was born. So they had to use computational tier, but we'll use the notation of FHE since you're all familiar with that notation. So intuitively, why does this work? Well, the prover, when he tries, if you think of Shai's gloves, when you try to answer Q1, when you manipulate Q1, you only see Q1. So, A1 is only a function of Q1. When you manipulate Q2, you're only a function of Q2. So it seems like it should work. This should be sound. Okay. So let me try to prove it to you, actually. Let's do the proof. Okay, how do we prove security in our soundness in crypto? By reduction. So suppose we have a cheater here that cheats, a cheating prover. So what can he do? He cheats. Two options. Either his answer 1 is indeed only a function of the first query, and answer 2 is only a function of the second query. Maybe he cheats this way, in which case, well, you broke the multi-proof interactive proof. You can't. You can't cheat like this. Okay, so that's one case. The other case, so I have no idea how this adversary works. I don't want to assume anything about this adversary. Okay, he may be inefficient. I don't know what he does. Okay, but either he acts locally on each query. So A1 is a local. It only depends on Q1. A2 is only dependent on Q2. In which case, you can use that to break this scheme, because you can behave like this adversary in this scheme and break the security of the MIP. Case 2, what if he's not local? What if somehow he manages, I don't know how, somehow he manages to give an answer that depends on both queries? In this case, I want to say, well, you broke the encryption scheme. Because so how do you break the encryption scheme? You open only this lock, you don't open this lock at all. And now you learn something about Q1. Okay, because A2 is the function of Q1. So you learn something about Q1. Done. Proof.
There is a bug.
There's a bug. Anybody see the bug? It's a subtle bug.
Cynthia is
And where's Cynthia? She's not here to tell us about the bug. So you'll have to come up. She's not here to help you. Okay, I'll show you the bug. So the bug is, what they notice, there's a third case. What is the third case? What if A2 is a function of both queries, but it's a randomized function? It's a randomized function, so that A2 as a function, it really depends on both. But the distribution, if you think about it as a distribution, it doesn't depend on the other query. So the distribution of A2 is the same no matter what Q1 is. But as a function, it's a function of both. And this kind of strategy is called no signaling. That essentially means that A2, it has the same distribution no matter what Q1 is, so it doesn't signal information about Q1. You can't look at it and say, oh, now I know what Q1 is and therefore break the encryption. It doesn't signal information, but it's still not local because it depends on both. Now at this point you can say, well, how is this useful? Well, can he really cheat in this way? How can an adversary cheat by using, practically speaking, only depends on Q2. Look, it's the same distribution. No matter what Q1, it's the same distribution. So why would it help him cheat? So let me show you actually that these type of strategies are very powerful. They can help the adversary cheat. And let me give you it by an example. So consider a very simple two-proof interactive proof for the three-coloring language. Okay? So the prover wants to prove that this graph is three-colorable. The two provers, that's what they need to prove to the verifier. How does the verifier check this? He gives them two random vertices that are either adjacent or the same. And he expects to get colors, two colors. If the vertices were the same and the colors are the same, he accepts. If the vertices are adjacent, he accepts only if the colors are different. So it's a very poor soundness condition, but still, if the graph is not three-colorable, you can't always cheat, that's for sure. There's no way that these two provers will succeed in cheating with probability 1. Now I'm going to show you how a no-signaling prover can always cheat with probability 1. How? Here's what he does. A randomized strategy. If the vertices are different, he gives distinct random colors. If they're the same, he gives the same random color. You always accept him. Always. And now note, if you look at one color, the distribution is random. Doesn't matter if the other vertex is the same vertex or it's a neighboring vertex. The distribution of each color here is completely random. He doesn't give you if you see this color, it doesn't give you any information about the other vertex, whether it's the same vertex or a neighboring vertex. So what if our adversary here, now do a delegation scheme out of it, and this is how the adversary magically cheated. How are we going to use him to break? So you can't use him to break, the multi-proof interactive proof because he's not local. But you also can't use him to break the FHE scheme.
So, yeah, this is not a strategy that he can. Okay, I see. This is not a strategy that he can apply on a FHE scheme, right? Because you need to compare what.
I don't know how he can do it, but I don't know how to prove that he cannot do it.
Yeah. So it's a problem with the proof.
It's a problem with the proof.
So, okay.
Yes, the proof fails.
And there are encryption schemes for which you can implement actually non-signaling strategy. I mean, without breaking, is there like an FHE scheme for which you can actually implement a non-signaling strategy?
That's a very good question. I don't know the answer to that. I don't know. There's a good question to come up with a FHE scheme that's resilient to such a thing.
Assuming IO, we have counterexamples to everything.
Well, assuming IO, come on. No. Okay, so let me think if we. Okay, let me just. So what we do, let me just finish this. If we had an MIP that is secure against such no signaling strategies, so what we do is say, suppose I had an MIP that I know you cannot cheat with these strategies. Then we're golden, we're done. Why? If you had a cheating prover here, look, two options. Either he's signaling or he's no signaling. If he's no signaling, you can use him to break the MIP, because this MIP is secure. If we assume that it's secure against no signaling, if it is secure against no signaling, we're done. Case 2, this adversary actually signals information. If it signals information, you can use him to break the FHE. Look at A2, it actually gives information about Q1. So you use this information to break the FHE. That's the high-level idea. Let me just mention what I'm hiding, okay? So what do you mean break with signal? You need to signal enough information, not enough to signal negligible amount of information. So it's not enough to just have signal, you need to have like some delta signaling. You signal some delta amount of information. So this is not as I'm hiding here this kind of factors. And also, I said the quasi-poly thing, where does that come up? It comes up because when you signal information, not necessarily you signal it efficiently. So the distinguisher here is not necessarily efficient. So that's where you need the quasi-poly instead of the poly. But I'm hiding this under the rug. This is the high-level idea. Okay, QED. So what remains is to construct this no-signaling MIP. And what we're going to do in the next hour is, first I'm going to show you I showed you the picture of Einstein, because I like it, but it's actually connected to physics, this notion of no signaling. So I'm going to show you the connection to physics, and then I'm going to talk a little bit of the construction, how we construct this no signaling multi-proof interactive proofs.